Good morning. Welcome to Krishna's class. Today's talk, we look at the geometry of linear functions over a vector space. The geometric perception is a way of understanding the concept in depth. So let us work on this. Now it's a prelude or something like a preliminary to understand the Banach theorem, which we have in our mind to consider in the next few lectures. Okay, so let us start with the discussion and let us set the condition. So let X be a linear space over K. Now K stands for either R or both are fields, and simply says X is a linear space over R or X is a linear space over C, depending on your vector space is a real linear space or a complex space. Now observe that K is a one-dimensional vector space over now we can define what a linear function is. Definition: a linear function on X is a linear transformation from the vector space X into the linear function is trivial, that means the zero linear function, then it is a map from X onto the zero element of it. Otherwise, it's a linear map from X onto it. So there are two situations here: either it is into or onto, properly into or onto. And it is into only when the map is the zero linear transformation. Okay. So essentially, if F denotes the linear function, then F is a map from X A, which is linear. That means it's a linear map from the vector space onto or into the associated. This is what is called a linear. Generally, this is called a linear transcription. But the special, because this particular linear transmission has some significance, and therefore we consider it in a in depth here, and it is also given a name. It's called a linear function. So the moment you say it's a linear function, it is a linear transmission from the vector space to the associated field. That is either R or C. We are only bothered about these two at the moment. Now, let us give some example. Consider x R3. It's a three-dimensional real vector space. Define it's easy to check that this is where are real numbers. Now it's easy to check that f is linear, that is we can verify. Belonging to so it's an example of a linear function. So in fact, you see that at the outset itself, these three numbers fix the linear function. In fact, we can see this the following. More generally, one can actually get a form kind. Finds the okay. That's an example. A second example would be consider C0. All continuous functions. Now define equal to some ht where h is a continuous function. So h some fixed element down then f is a linear function. sorry, determined by the function. In fact, you can take H to be identically equal. And of course, trivial one is that f from x to k pi by is trivial linear functional on that is the function which maps every vector to the zero element of K. This is what you call a linear function or the zero linear functional. Okay, and this is also great when you consider the structure of all linear functions. Now let us. Now we shall see more examples. Now I will just make one mark or I'll do the following thing. This is for belonging to some index set now. Very then any x is a linear combination of elements in that is a finite linear combination of the type A alpha where x is equal, where see we have not put any structure on this. We have not put any structure on the linear space, and we are not in a position to talk about an infinite sum without any, unless we can introduce some kind of a convergence notion on the space. Okay? Therefore, this is we are at the moment talking only about a finite sum. That is the meaning of that. And this is an important point. At the moment, we are not talking about normally linear space. We are not talking about a topological vector space. There is no topology to support it. See, the moment you want to talk about infinite sum, you should have some kind of a convergence notion which can be justified. Okay? So we shall, for the time being, avoid that and then just write. It's a finite sum, there is no problem. Finite sums are well defined. Finite sums of vectors are well defined. Yeah, vector space. So that's a comment I want you clearly understand. Okay, now this is quite easy to understand. Okay, so uh, remark can at the moment talk about a finite sum because we have not introduced any topological structure of the space. So this is a special remark that now we now state the theorem. A linear function on a space X is completely determined by take by the values it takes on okay. So we shall just write the next. Then x is equal to sigma, say some a alpha x alpha, where a alpha belongs to it's a finite. Finite. Now suppose f of x alpha c alpha, where of course belongs to then fx is equal to alpha belonging to lambda a alpha x alpha, and this is equal to sigma alpha belonging to lambda a alpha. So what it means is that if x is an element of capital X, and if x has a representation like this, then that simply means that only for finitely many alpha, a alpha is different from 0. So that this is a finite sum, otherwise it would be an infinite sum, which has no meaning. Okay? So only finitely many a alphas are 0 or non-zero. Different from 0. Therefore, this is essentially a finite sum. Now, suppose you have a f is a linear function. It is defined for every element of x, and in particular for x alpha. So, f of x alpha is a scalar, and let that be given by c alpha. Then what you get is this. Because of the linearity, f of this sum is essentially equal to sigma, the finite sum that you have, a alpha f of x alpha. That is the linearity that comes. And because of the linearity, you see that this is f of x alpha is already fixed, that is c alpha. Therefore, this is sigma a alpha c alpha. And you see that every linear functional is completely determined by the values it takes on a basis. And you see that once you fix the basis, the representation for every vector is a unique representation. Okay, right? Because this collection is a linearly independent collection, right? And therefore, see that this is a unique representation for x, and therefore you see that f of x is given by this. Okay, this proves the values on each element of so you need not know the value of the linear functional at every vector. That can be computed once you know the values of the linear functional on a basis. That is the form of the story. Now let us take a let basis for where VIF okay. Now what do you get? Get the following. F of so then x is equal to say x1 e1 plus x2 e2 x3 e3 is the unique representation where xi belongs to this is the unique representation of x in terms of the basis e1 e2 e3. Okay? And this is often identified as belonging to R. Okay. Now let f such that f of and f of e3 is equal okay. Then what do you have? F of x this is equal to x1 a1 x2 a2 or we will write it as this is equal to this, or we will write it as a1 x1 x is equal to this is the representation for a linear function. Now you see that there is no sanctity for the choice of one E3. One can choose any ordered basis, say U1, U3, three vectors, three linearly independent vectors in R3, and then give a representation for every x, which will be of this form, I replaced by Ui, and then you have, if you know f of U1, f of U3 is fixed, given is fixed as some scalars, then you get the f of x is given. So there is no sanctity about choice of 1, 3, but we are used to. Now let us have a look at this. Just we'll try to an interpretation. Now observe the following. The following geometric facts about the linear functional what is that? The first thing is f of x equal to 0 was if and only if a1 x1 plus a2 this is in R3. You know that x1, x2, x3 are the arbitrary coordinates, coordinates of an arbitrary. Okay. So we have, in fact, And what is this? This is plane except in this equal to 0. Whose equation is rho mass equation. So it's a plane that passes through the earth. Okay, that's first thing. That is the observation. Now you know that to fx equal to 0, two-dimensional subspace. That means the set of all points. So you can denote it by M. Of course, I take F log. Then M is a plane non-trivial subspace of fact dimension of M is 2. Of course, the trivial situation, it is a whole space. Okay. Core generally in X F is 0. C that is a trivial situation. Now we shall make some more observations and then later we formulate the general. So let us. So you take R3. Now to have a plane M is a plane. So this is M passes through the origin. Suppose this is 0 and working in P. Now let us make the following observation. Choose any plane origin 3 determined by the vector 3 such that B1 square plus B2 square zero. That means this is not the zero vector. Zero vector. This I mean a vector. Now define set of points 1, 0. I can rewrite the whole. So define f at 0. This is equal to 0 because f of k is 0. So M is a two-dimensional of. Now let us define for f of x3 instead of then f is linear So what do we have? So we started with a plane passing through the origin. From that we constructed a linear function. So from the construct a we shall say that M the manifestation of a linear function. Of okay, that means M defines a linear function. Does the geometric image okay. Now let us investigate further. Go into some depth on the geometry. So that will some insight. Now observe the form. So we have now if you take a vector, say alpha. Now what happens? Suppose you translate this to vector alpha. Then what happens? Now look at the translator. Not you. Given by alpha not in L. Alpha does not belong to subspace. I equal to the or I'll write it. Yep. Say m plus alpha. M plus alpha then this is essentially this will be the following. What is this? This is equal to I got f of y okay. So let some constant plus thus you see that in fact you see that any y plus x belong to and in fact this sum is parallelogram of x plus alpha is take this as alpha what you do is you just sum it up so this is x plus this vector is x plus complete the parallelogram and the diagonal x belongs to m and alpha does not belong to alpha not equal to 0 alpha does not belong to simply say alpha does not belong it's enough and it, because 0 is always okay then you can sum it up so this is what you therefore f of x plus alpha is equal to f of x plus f of alpha that is equal to f of x plus c. So what is that? Okay. So you look at this. Now you see that translate to vector. Okay. So if you want a pictorial version of this for R2, then let us just digress a bit and go to consider R. So this is ordered basis for that. Now you see that suppose now f of x equal to 0, this is a1 x1 is a plane passing through the. So let M be zero. That is the, this is essentially all x1 with this property. So M is a one-dimensional and all one-dimensional subspaces are not equal to 0. I am assuming that is a1 square plus a2 square is not equal. I am assuming I take f not equal. That is a1 square plus a2 square is not equal. Then that means a1 and a2 are not equal. So a1 x1 is a2 x2 is a plane passing through. It's a line passing through. Thus the geometry is this. This is M. And now suppose you choose an alpha. Alpha does not belong. Then M plus alpha easily we know from vector analysis. This is M plus alpha. Is a line parallel to M passing through alpha. Okay. So essentially you see that the value of any y belonging to M plus alpha is x plus is the value of f on any y belonging to M plus alpha is y is equal to x plus alpha for some x belonging to M, and f of y is equal to f of x plus f of alpha, okay, which is equal to f of y. So for any y belonging to M plus alpha, that is the line parallel to M, the value of f is given by a constant. Okay, so you see that by taking different vectors, you can get all planes M plus alpha for the given M. So given M, so and M plus alpha is not equal to M plus beta, then alpha minus beta does not belong. These are all the geometric facts about this. All these have some significance in whatever we are going to generally. Okay. So you see that there is a similar, so this is the scenario that you have. So you see that essentially for every vector y belongs to plus alpha, f takes the value of, okay. Now if you consider this, now consider the single vector alpha, alpha not equal to 0. Okay. It's not identical because the moment you have assumed that alpha does not belong to M system and the M direct sum vector space span by that means it is CR. So you get this all lines parallel to M by taking different values for alpha, or you have chosen the the span of alpha is a vector. So you see you have this what different color. See that this is the rank of it. Through each point there is a unique parallel. Okay. Through each point there is a unique thing parallel to M. And what more you have? In x belonging to is German. You have to you recall the geography. Right? If R2 suppose this is your alpha, so you take k alpha, then this is the line parallel. What more you have? So take any x in plus k alpha, if you use this, try and use k only. Let's see. How this k I will see. So y is equal to 3 times and this means that for every point you know this. So once m is fixed, you can define a linear space, sorry, a linear function whose null space is the value determined by point and the value of f. So this is the geometric interpretation linear function. Now we will try to generalize these observations. Okay. So in the case of R3, passing the origin and the value of linear function at any point is determined by So this is the percentage. So in short, I think so. This is what we therefore, and I think it is much easier to understand the geometry if you work out on. So let me conclude today's lecture, and we now try to do it the general. That will be the next lecture. So let me just designate next lecture. So thank you very much.